number 2 is titled Free Vibration of determination of the frequency of vibrating. And I think it was in the lecture anyways, you know, when we talked about the spring. That was like this, right? Okay. And then what we did is we added a mass to it, right? M. Then what happened? We had a deflection of delta static. If I do a free body diagram on this mass, what do I have? I have mg, right? And then k delta st, and because it is in equilibrium, that means that mg is equal to k delta st. And we know from the equation of motion of this guy, you will get, you know, after it gets displaced, right? It's mx dot dot, right, plus kx is equal to 0. And we know what the natural frequency is, right? It's the square root of k over m. Based on this equation, what is k over m equal to? K over m should be equal to g divided by delta st. That means that omega n, the natural frequency, then if everything is correct, should be equal to the square root of g divided by delta st. So what is this telling me? It's telling me that if I have a spring that I'll give you of unknown stiffness, an unknown mass, you just put it, you just hang it, you pull, you put on it, you hang on it, I guess, an unknown mass, and you measure a deflection, let's say 2 centimeters or 3 centimeters. Technically, if you plug it into this equation, you should get the natural frequency. Boom. Now, we're going to do that, obviously, but how are we going to verify that it is true or not true?
Because we already know what they are.
Because by the, you know, so we will put the mass at the end of the spring, we will measure the deflection, right? And then maybe in class, we'll just calculate, okay, what is that frequency? Because you want to get as much as possible from the thing. And then to verify if it is true, we will pull the mass from equilibrium and then measure maybe 20 cycles.
Sweet.
And then divide by that, find what the period is, and from the period we can find the frequency and then compare the two numbers. That's what this lab is all about. So straightforward, no biggie, no stuff. Then we move on to lab number 3. Lab number 3 is again that same situation. It's titled Free Vibration of Single Degree of Freedom Systems, right? So we have found that the frequency again takes up this form, square root k over m, right? So this is the, for lab number 3, that's what we're going to be looking at. So in other words, we're going to be looking at what happens when you increase the stiffness. Obviously, when you increase the stiffness of a spring, the frequency should go up. When you increase m, the frequency should go down. But it's not going to go down just any other way it wants. It has to go down according to this, because now we're going to know exactly what the mass is. We're going to know exactly what k is. In fact, you can plug those numbers in your calculator, find what the frequency is, and then the test is going to tell us if it is correct. So we're going to do few variations of k, few variations of m, just to get kind of a nice combination, and that should be done.
All right.
So I think that's, I think we should be
20 minutes.
I don't know how long this is going to take. It may take a little longer, but it's actually here. That's what we're going to be doing.
Dang it, Mark.
Hey, you know what? I don't need that. I don't need that from you.
Feeling good?
Oh yeah, oh yeah. Rock solid, man.
Mark, you little son of a... I got that song stuck in my head.
I know, because it's awesome. No, I don't need that. Oh, just half. Here we go. It's really a 7 minutes.